This is the first lecture on Text Unit 9, which is on gases and gas laws. Now remember, laws describe the behavior of gases. This lecture in particular is on process gas laws, so it will be about descriptions of how gases behave in processes. All processes have a before and an after, and it's the before and after that we are principally going to be interested in here. At constant temperature, the product of a gas's volume of pressure is a constant. Now that's written PV equals B. This is called Boyle's law. That's why I use big B for the constant. In process form, or to arrive at an equation for process form, consider that this PV will always be B before and after any process, or PV before equals PV after, or P1V1 equals P2V2. This is the common process form of Boyle's law, relating pressure and volume of a gas before and after a process. Right, at this point, we should talk formally about what pressure is, although most people have an informal understanding of what it is. Formally, pressure is force applied per unit area. The SI or metric unit of pressure is the Pascal. Common units, which you're probably more used to hearing about for pressure, are atmospheres, abbreviated ATM. We will use those in this course. Inches of mercury, which often appears on the Weather Channel and barometers in the United States, or millimeter mercury, which is a unit appearing on laboratory barometers. Millimeters of mercury are abbreviated mmHg, millimeters of mercury, or often called torr. It's an important relationship that 1 atmosphere equals 760 millimeters of mercury, or 760 torr. If you want to hear of a force per area definition of pressure, that's pounds per square inch. Common English unit you've probably heard of for pressure. What Boyle's law says in words is that pressure goes up and volume goes down. Here is the equation again. P1V1 is P2V2. This actually shows the molecules of a gas moving around, which they do freely, and the molecules in a gas are far apart from each other. More on that in a later lecture. But what this cartoon is supposed to illustrate is that as this piston comes down, the pressure applied to this gas goes up, and naturally its volume goes down. And here we see a V1 and a P1, and a matching V2 and P2. Well, what we see in this picture is that the volume goes down, pressure doubles. In this model, you have to understand that pressure is caused by the banging of these gas particles against the walls of the container, and as the volume goes down, they do more banging against the wall. Again, we will discuss this we'll discuss this idea about pressure again in a later lecture. Here's an example of a typical Boyle's law problem, in fact selected from the list of exercises, which I will put up. A container holds 500 milliliters of carbon dioxide at 20 Celsius and 742 torr. What will be the volume of the carbon dioxide gas if the pressure is increased to 795 torr? Right, you should attempt this before moving on to see the solution. The way to approach this sort of problem is to assign variables. P1, the first pressure is 742 torr, and the second pressure is 795 torr. First volume is 500 milliliters to 3 sigs. What is the second volume? T1 and T2 are the same, more about what kelvins are in a moment, and constant temperature, no change in temperature, is a prerequisite for Boyle's law. So we can apply Boyle's law. P1 V1 is P2 V2. We know we're solving for V2. Rearrange the equation algebraically. V2 is P1 V1 over P2. And then put in the values of pressure, 742 torr times 500 milliliters over 795 torr. The torr units of pressure cancel. And the answer is 467 milliliters. So as the pressure goes up, the volume goes down slightly, as we expect. Note that we can use torr units for pressure as long as we use them consistently. And any units as well are acceptable for volume. Charles' law for gases states that at a constant pressure, the volume of a gas increases proportionally with the absolute temperature. You could write this as V over T, volume over temperature, is a constant C, or to make it a process, before and after, V1 T1 equals V2 T2. VT before equals V over T after. Okay, it's important to understand what's meant by absolute temperature in this gas law. Charles' experiments with volume and temperature first found the true zero, the lowest temperature possible. Now, he did that by plotting the volume of a gas at several temperatures and making a line which he extrapolated back to zero volume for the gas. He then predicted, negative 273.15 Celsius would be the lowest possible temperature. An absolute temperature scale, the metric absolute temperature scale, has zero at its lowest possible unit. The scale is called the Kelvin, and you can make a Kelvin temperature just by adding 273.15 to the Celsius temperature. By definition, this is an exact relationship. So in a metric absolute temperature unit, 0 is the lowest possible value. And there will be no negative values. Okay. For example, a container holds 50 milliliters of nitrogen at 25 Celsius and a pressure of 736 millimeters of mercury. What will be its volume if the temperature increases by 35 Celsius? Again, write down variables. Pressure's the same before and after, which means we can use Charles' law. First volume is 50 milliliters, and the second volume we don't know. That's what we're solving for. We get our first temperature, well, we simply convert to Kelvin by adding 273. 273.15 is exact, but this only is exact to the ones place. So we keep our answer to the ones place. Second temperature is 35 degrees bigger than the first temperature, so we add 35 degrees to 298, or we can calculate it this way. Again, precise to the ones place, that's 333 Kelvin. V1 T1 is V2 T2. Solve for V2, which is V1 times T2 over T1. Plug in numbers, that's 50 milliliters times 333 Kelvin divided by 298 Kelvin. Notice the Kelvins cancel. And we arrive at 55.9 milliliters of nitrogen. Right. No, we could use any volume unit we like for Charles' law as long as we use it consistently for V1 and V2. But temperatures must be in absolute units. And the metric absolute units that we will use are Kelvin. It's also possible to define a gas law at a constant volume. The Gay-Lussac law observes that at constant volume, pressure increases as temperature increases. Excuse me. Or P equals G times T, which you can naturally write P over T is G, make it similar to Charles' law. Or in process form, P1 over T1 equals P2 over T2. Right. Now, again, absolute temperatures are required for this law, and it's true at constant volume. Right, here's an example. 10 liters of gas is found to exert 97.0 kilopascals at 25 C. What would be the required temperature in Celsius to change the temperature to standard pressure? And to answer this, you need to know standard pressure is 1 atmosphere, or for this problem, for us, it's 101.325 kilopascals. All right, this, by the way, is the relationship between pascals and atmospheres. We'll just use kilopascals as our pressure unit, and you'll see that any pressure unit is acceptable. So P1 is 97 kilopascals, and P2 is 101.325 kilopascals. Temperatures require absolute units, so we convert to Kelvin. 25 Celsius plus 273.15 is 298.2 Kelvin. And we're solving for the final temperature, T2. Okay, arrange the equation algebraically. T2 is T1 times P2 over P1. And plug in units. I have 298.2 Kelvin. In parentheses, I have P2, 101.325 kilopascals over 97 kilopascals. This is to illustrate that the pressure units of kilopascal cancel. And the answer we arrive at is 311.5 Kelvin. Now you have to be careful about this sort of thing because the question is about Celsius. And 311.5 minus 273.15 gives a temperature of 38.4 Celsius for our solution. For any given amount of gas, and we've been assuming throughout all these gas laws that we're talking about a certain, a given amount of gas that stays the same throughout the process. Right. For any given amount of gas, if it stays the same throughout the process, PV over T, pressure times volume over temperature, is a constant. I just call that constant C here. You could write this as P1V1 over T1 equals P2V2 over T2 in process form. And this is called the combined gas law. Okay. Now the combined gas law contains the Boyle, Charles, and Gay-Lussac laws. Here's the combined gas law again. Now consider, if temperature is constant, T1 equals T2, P1V1 over T1 equals P2V2 over T1. You can multiply both sides by T1, remove it from the equation, and get Boyle's law. If pressure is constant, P1 is P2, and P1V1 over T2, T1 equals P1V2 over T2. You can divide pressure from both sides of the equation and get Charles' law. Likewise, it's not shown here, but if V1 is V2, those will cancel on both sides, and you see that P1T1 equals P2T2. So the combined gas law actually covers Boyle's, Charles, and Gay-Lussac laws. And in addition, allows prediction or calculation of situations in which all three of these variables are changing in the process. Here's an example. 2 liters of gas is collected at 25 Celsius and 745 millimeters of mercury. What is its volume at STP? STP here is a common abbreviation for standard temperature and pressure, 1 atmosphere and 273.15 Kelvin exactly. Solution using a combined gas law. P1 V1 over T1 is P2 V2 over T2. Write down variables. V1 is 2 liters. T2 is 25 Celsius, 298.2 Kelvin. P1 is 745.0 millimeters of mercury. T2, we've been told, is 273.15 Kelvin. P2 is an atmosphere. And here you should remember that an atmosphere is 760 millimeters of mercury. And that's an exact number. We're solving for the final volume, or V2. If we rearrange the combined gas law equation algebraically, V2 is P1 times V1 times T2 over T1 times P2, or 2 liters times 75 torr over 273.15 Kelvin, 2 liters times 745 times 273.15, sorry, divided by 298.2 Kelvin and 760 torr. Now I've put 760 torr and 273.15 Kelvin in italics to remind us that these are exact numbers. Using the multiplication rule, we'll get 3 sig figs in our answer. Torrs cancel. Kelvins cancel. The answer is 1.80 liters. And this concludes the first lecture on gas laws, or Unit 9.